In this chapter, we are going to talk about time step and velocity calculation. So now we're going to talk about time step because we will use it later. So I think it's really important to understand it, and I've prepared an example to clarify what it is. So let's copy paste it like this, and dive inside. So let's see the viewport. Okay, so here is a basic sphere, and the transform to animate it over the x-axis, and a trail to compute the velocity. So if I play it, I have something like this, and if I go to the geometry spreadsheet, I can see here the velocity attribute, and it's 1. So it's 1 meter per second, and this is important because if I check the geometry there, I can see it starts at the frame, let's say 0 here, to the origin, and at the frame 24, it's finished to the 1 meter. Okay, so it's 1 meter per second because the FPS is set to 24. But what happens now if I want to timesheet it to the frame 0 and add the velocity to the position like this? Okay, I'm just taking the velocity from the second input, which is this one, so the trail, and I am adding the velocity to the position. So let's check what happened. And as we can see there, it's doing 1 meter per frame and not per second. So we need to convert the velocity from second to frame by multiplying with the time step. So here you have the time step. So it's basically 1 second divided by the substep times the FPS. So we have something like this, and if I increase the substeps, you can see the time step is changing. Okay, and now if I just move it to have a better visualization, and I multiply the velocity by the time inc, so the time incrementation, let's see the result that I have with merge. And it's following, it's the same position, which is what we want. So now let's check another example, which is the vel calculation, and let's copy paste it like this and dive inside. So in this example, I would like to show you a different way of computation for the velocity and why we should use this one. So I have just a box there like this, an assemble, and a .NET simulation. Okay, inside this is very basic, ABD packed, the bullet solver on the ground plane, and I've added an initial velocity on the y-axis plus an angular velocity on those axes. So this is the result we have. Okay, very basic but useful. So if I just import and create points to represent the object with a transform pieces, this is what we have, and this is correct except for the frozen geometry, let's say. Yes, better. And if I check the velocity, okay, let's have a black background and maybe a better scale vector. Okay, so this is what we have. But if I compute the velocity with this one, for example, with a trail and with a central difference, it will be different. As you can see, it's a bit different on this example because the central difference is the most accurate. If I go to the backward and like this, you will see it's more visible, and same thing for the forward. Okay, so here is some example that I've done just to show you how it's computed with the trail. So basically this is a time shift with $f plus 1 for the forward difference. So if I go there, I just import the position from the second input, so the $f plus 1 plus and the position, my position, subtracting it and divide the result by the time inc. So this is why I've showed you this example before. So, and this result I just plug it to the velocity, and this is what I have with a switch and a trail in the forward difference. Okay, so it should be the same, and it is. If I go there and I take it off, it's not. I go back to the previous one. So same thing for the trail for this one, but with the backward difference. It's not anymore time $f plus 1, it's $f minus 1 with the same thing, but you have to invert the subtract and divide to the time inc as well, to the velocity. And for the central difference, it's a bit different. We have to time blend the position, get the time shift $f minus 0.5 and $f plus 0.5, and then to import those two positions, subtract it, and divide by the timing to the velocity as well. So this is what we have, and if I go there with the trail to the central difference as well, it's the same velocity. Okay, but this one is computing the velocity. If we go inside allow editing, it's computing the velocity with the angular velocity, so this one with the code here. So you have different way, let's say, and it's taking the velocity with the cross with the angular velocity and some different operations, and adding the velocity from the point as well. So this is the velocity we want to use, because this is the most accurate. I just would like to try another frame just to be sure about it's way different. Yes, as you can see now, it's really different. So this is why we need to use these transform pieces for computing the velocity. So let's go back to our effect and continue.